Okay, gang, welcome back. Happy Friday. We are starting on page 73. We'll take our look at the calendar. Lots of stuff going on right now. So first of all, the arbitration project was due last time. If you turned it in to me, I have handed it back. Hey, gang. If you have turned the project into me, I have turned it back to you. If you have not yet turned it into me, throw it in the folder. If you've got it done, I do take them up to 1 week late with varying penalties. Also, trucks is officially due right now, so if you've got it done, throw it in the folder for me. Again, I will take trucks up to 1 week late with varying penalties. Today we were talking about something called the second derivative. On Monday coming up, it's the review for our first test, which is scheduled for Wednesday. That test is going to be on everything we've done this semester, including what we do today. In terms of studying for the test, it is not too early to start. Don't wait until Tuesday night to study for Wednesday morning's test. So the test, there are lots of resources for problems for you as you prepare for this test. There's the homework problems that I assigned. There's plenty of homework problems I didn't assign. There's lots of opportunities to get more practice with each section in the textbook. Also, if you jump to page 84, page 84 in this packet is a collection of sample test problems for which there are YouTube videos of me solving each of them. That's on page 84. Yeah, I think that's good. Any questions about our schedule? Okay, and one thing to note about the test is that you are welcome to use a cheat sheet during the test of your own creation, anything you want on it, one page, front and back, but no other resources. All right, okay. All right, let's get started. Okay. So here we go. In this class, we calculate and interpret second derivatives. For y equals x cubed minus x, let's find all of these things. Y of 2, y prime of 2, y double prime of 2, and y triple prime of 2. Okay, so y of 2 is, sort of an uncommon way to write this thing, but I'll write it like it's function notation, like f of 2. And let's go ahead and calculate. So here we just plug in. So we go 2 cubed minus 2, and that is 6. So y of 2 is 6. Next up, in order to find y prime of 2, well, I first need to find y prime of x. So what is the derivative for this function? 3x squared minus 1 is good. And then we're going to find y prime of 2 by plugging 2 into that function, right? That derivative function. So I got 11. Okay, but then it says y double prime of 2, and we have not seen y double prime before, but it just means take the second derivative, derivative of the derivative. This 3x squared minus 1 in purple, it's y prime, but I can just think of it as a brand new function, right? It's a perfectly good function on its own, and it has a derivative which we calculate as normal. So what is the derivative of 3x squared minus 1? 6x, right? And then the minus 1 disappears. That is the derivative of the derivative, second derivative. And again, this problem asks us to plug in 2 for the x. So 6 times 2, 12. All right, and that was so much fun. We can do one more. Y triple prime is just the derivative of the derivative of the derivative. So I'm just going back to my 6x and taking one more derivative. It is 6. Still supposed to plug 2 in for any x that I see. What do I get when I plug 2 in for every x? I get 6. It's just 6 no matter what x is. So that's the third derivative. I didn't ask for it, but what's the fourth derivative? 0. What's the fifth derivative? 0, and every derivative from that point on is 0. Okay, so it turns out we can do this, some of this anyway, on the graphing calculator. So don't take yours out now. I'm going to do this real quick, and I don't expect you to follow along on your calculator, but you can check out the video if you want to see the details. I'm going to go into, what am I going to do? not here yet. Okay, I'm going to go to math, and then all the way down here it says n deriv. That's the calculator's way of saying take the derivative of. So in this case, the function was x cubed minus x. So I type in x cubed minus x, comma. This is just the syntax. You always have to tell it what the variable is. It's almost always going to be x, but you got to put it there anyway. And then you got to tell it to plug in the x value. In this case, it was 2. So there's our syntax. Function, variable name, it's almost always going to be x, and then the value of x. And what are we expecting is the answer for y prime? 11. Yeah, it's close. Again, the calculator is not doing any calculus. It actually does not have any idea that 3x squared minus 1 is the derivative. What it's doing is finding a secant line that's really close to the tangent line, and it's off by not much. Okay, so that's one way to do it. Another way to do it, and on some of the more modern operating systems for the graphing calculator, the syntax will come out looking a little bit different, a little bit more friendly, like that. Okay, and then, okay, we're not going to do GeoGebra, we're just going to do the other option here. Again, you can check out the commands later on. But I'm going to type in the original function way down here in y0. So that was, again, x cubed minus x. And then up here in y1, I'm going to tell it to take the derivative. So it's, again, math and then number 8, same command that we had before. But I'm not going to type x cubed minus x. I'm just going to tell it where that function is. And it was all the way at the bottom, which is called y0. It's inside of bars, and then over to the right y bars. And the first option is function. And then all the way at the bottom, we'll find y0. And so it says, take the derivative of the function that's typed down there at y0, comma x always. And then comma, now I'm gonna, you could put a 2 right here, but I'm actually gonna do something more general. I'm gonna put an x. Okay, so that's fine there. And so then if I ask the calculator, so again, y1 stands for the first derivative. So I'm gonna ask the calculator to tell me y1, y prime of 2. What was y prime of 2? 11 is the right answer. Again, it gives me the almost right answer. But doing it this way actually allows me to come down here and I can say, hey, why don't you put here the derivative of this guy, which would be the second derivative of the original function. And so it's the same general format, math, and then 8. And now I'm just going to put a y1 right there, and then comma x, comma x. Great. And so then if I ask the calculator to find y2, that would be the second derivative. What is the answer for this one? Second derivative at 2? 12. I'm hoping to see something around 12. Hey, it got better. All right, so I got the second derivative perfect. It was pretty close on the first derivative. Let's try one more time. We're going to push our luck. And right here, I'm going to do the derivative of which function? The derivative of y2, which is going to be what derivative of the original function? That's supposed to be the third derivative right there. Comma x, comma x. Okay, let's see. What's the answer for this last one, the y triple prime? It's supposed to be 6. Function or y triple prime of 2, 6. And instead, I get this anti-bird message. I don't know. What can I say? So the calculator is limited. It can do the first 2 derivatives and nothing more than that, all right? Okay, that is fine. Okay, and then, yeah, that's good. You can try this other one on calculators at home later. We're gonna move on. Okay, number 2, notationally, all these primes get unwieldy, and so we write higher order derivatives as follows. All of these things mean the fourth derivative. It would be awkward to write y and then 4 primes up there. Hard to write, even harder to read. So all we do is we put the number 4 and then in parentheses. So that indicates that it's not the fourth power, it's the fourth derivative, so the parentheses. Same thing over here at the far left, f, fourth derivative, that's like 4 primes in parentheses. This thing in here, students kind of get confused about this. Like, okay, they buy that there's a 4 and there's a 4, but it seems like we're putting the 4 in fundamentally different spots, right? Like on top, the 4 is on the D, but on the bottom it's on the X, and that doesn't feel fair to some students. And so I'll just point out that this right here is our notation for take a derivative of, right? And this is our notation for take a derivative of. And so if I just say, hey, take a derivative of my function y, and then take a derivative of that thing that I just took a derivative of, right? What order derivative is this? This is a second derivative, is what this thing represents. Now, if I just treat these guys as being like fractions getting multiplied, then I have a d times a d. What's our way to write that? D squared. And then there's a single y. There's not two y's up there. So there's a single y. Then we're going to treat the dx as being like one quantity, even though it's two letters. I'm just going to call it one thing. So it is a dx times a dx, which I can write as dx squared. And then we just get lazy and don't write the parentheses. And that's how we get to that notation, okay? So the two's in different spots for like a good reason. Okay, now we introduce a concept known as concavity. We're going to write the intervals of concavity for these three pictures. So this first picture right here, if I think about slopes of tangent lines, so maybe that one, and then maybe that one, and that one, and that one, and that one. And I just want to think about the slopes as a collection of numbers. Maybe this is like a -3, and a -1, and a 0, and a 1, and a 3, something like that. Just as a list of numbers, is that list always decreasing, always increasing, or like mixing and matching? That is an increasing list of numbers, right? And so there's something consistent. Even though the function itself, this parabola-looking thing, is going down and then coming up, that's not what I'm focused on. Just focused on the slopes as a collection of numbers. And when you have slopes that as a collection of numbers are getting bigger and bigger and bigger all the time, we say that this guy right here is concave up. And I'll just go ahead and put some intervals. I mean, it's concave up all the time, minus infinity to infinity. And then looking at the next picture, I will again draw 5 tangent lines. And so the slope here is maybe 3, and then 1, and then 0, and then -1, and then -3. We're always moving left to right on the x-axis. Yeah. So as a collection of numbers, what's happening with those? They're always, the numbers are always what? Decreasing, and we're going to call such a thing concave down. So this graph is concave down. Again, yeah, on negative infinity to infinity. Okay, and then the last one is fundamentally different. Let's take a look at it. So I will draw a tangent line here, and then maybe one right there, and then there, and then there. And so I'm just going to estimate the slopes of these guys. So maybe this first one's like a 2, and then, I don't know, like 1.5, and then like I think that one right there is like the shallowest. And then like it's like a 1.5, and then a 2, something like that. So always increasing, always decreasing, or mix and match. This is a mix and match, right? First it's decreasing to the left of the origin, and then it's increasing to the right of the origin. And so I don't have any other phrases. It's just a combination of concave up and concave down. So here on the left-hand side, that is to say any place that x is less than 0. What do you think? When the slopes are increasing, when the slopes are decreasing, yeah, negative infinity to 0. But when the slopes are decreasing, which one did we call it? That was concave down. So this is concave down for any x less than 0. And then the slopes start to increase again, concave up for any x is bigger than 0. Okay, but there must be some better way to think about where it's concave up and concave down without drawing 5 tangent lines on every graph, right? And so this first guy right here reminds me of like a cup, like it would hold water, right? You could pour water inside this thing and it would stay there. Whereas if you try putting water in the other guy, it would fall out. So the first guy is a cup. The second guy looks to me like a frowny face, upside down, not very happy. And so here's our mnemonic. If a graph can hold water like a cup, it is concave up. See what I did there? If the graph looks like a frown, then the function is concave down. Okay. This first guy, but you have to use your imagination a little bit, because in the beginning here, is it more cup-like or frown-like? It is frown-like in the beginning, so it is concave down in the beginning. And then at the end here, is it frown-like or cup-like? It is cup-like, even though technically, I guess, if you just started pouring water in here, it would drip all the way down, but that's because the behavior changed, right? That's part of a cup. It happens that we don't have the rest of the cup, but that's okay. All right, next page. Fill in the blanks. So the first two is old stuff for us. If f prime is positive, just imagine tangent lines that are going uphill. What is the original function doing? Increasing or decreasing? Original function is increasing. If f prime is negative, downhill tangent lines, then the original function is decreasing. So these first two things are old for us. But the next ones are new. It's a little bit of mental hurdles that we need to go through to get here. F double prime, positive. So I'm just going to translate. You don't need to write this down, but if I tell you that f prime is increasing, just like a brand new sentence, don't connect it to this just yet. If I just tell you f prime is an increasing list of numbers, like which of the first two pictures, purple or orange? Purple. F prime was an increasing collection of numbers, right? -3, -1, 0, 1, 3, increasing. Then concave up, right? That's what we've seen. But f prime increasing, then f is concave up. You don't need to write this yet. But if f prime is decreasing, f prime is increasing, I'm going to hide temporarily this little prime thing here. Would you guys agree, if you have a function that's increasing, then its derivative is positive? It's actually exactly what we wrote here. If a function is increasing, then its derivative is positive, right? Okay, well here, f prime is a function which is increasing. So its derivative is positive, agree? And what's a good way to talk about the derivative of f prime? What would we call the derivative of f prime? F double prime, right? So f double prime is positive. And so that's the connection here, is that leads directly to f double prime being positive. So this is really, like I said, mental gymnastics here. F double prime being positive means f prime is an increasing collection of numbers, means f is concave up. So that's what goes in our next blank. Concave up. And then the last one, Anji? That is not implied here. It could be that f double prime is increasing. That would be some reference to the third derivative, which I can't look at the graph and know what's going on with the third derivative, but that does not say, none of these things say that f double prime is increasing. That's like another level of analysis. Okay, and then the flip side, if f double prime is negative, the graph of f turns out to be concave down. Now, it is quite possible that you do not have like full comprehension of why those last two statements are true. That is okay. Take your time with that. But the fact is the last two statements are really useful shortcuts that I just want you to have memorized. Like I don't want you to have to play the mental gymnastics game every time you talk about concavity. F double prime positive is going to become synonymous to concave up, even if you missed the connection that we drew up there at the top. Okay. All right, so a little bit strange today. We're going to do like 3 separate demos. We just finished the first one. That was the longest one. I will call us back together at some point, but let's see how far we can get on the activities starting right there. So let's come together on page 78. Here we are. Here's a definition. A point on a curve. Y equals f of x is called a point of inflection for the curve if the concavity of the curve changes at that point. So point of inflection if the concavity of the curve changes at that point. So taking a look at my 2 pictures here on the left, in fact, the combined picture of these 2 looks a lot like the bottom left one on that first page, right? Like this picture looks like that bottom right picture. And on the far left, it's a cup, and in the middle, it's a frown, and on the far right, it's a cup again. And so we've got 2 places where the concavity changes. This first point, it goes from concave up to concave down, and then at the other point, concave down, switching to concave up. And so those 2 points are called points of inflection or inflection points. Okay, so how are we going to find the inflection points? Well, if the graph is concave up, then the second derivative is positive. And if the graph is concave down, the second derivative is negative. And so how much do you think the second derivative is where it changes? 0, because it's the only number that's between the positive numbers and the negative numbers. So what we do to find where the points of inflection are is to take the second derivative and make it equal 0. So let's try number 2. says find the intervals of concavity for that function right there. So let's go ahead and write in here, first derivative. Okay, who's got this one? 3x squared minus 16. You could set this thing equal to 0. That would find you the critical points and help you determine where the original function f was increasing or decreasing. But that's not what this question's after, so let's keep going. F double prime of x. Somebody else? And sometimes that's a positive number, and sometimes it's a negative number, and the place where it changes is where it is equal to 0. And so we set this thing, we actively set this thing equal to 0. We've been setting things equal to 0 for a few weeks now. This is the first time we were doing the second derivative equal to 0, and there's only one thing that we are after, and that is to find where it changes concavity, where the original function changes concavity. Lucas?
Could you accomplish the same thing by
Equal to 1. Why equal to 1? The slope is 1 at an inflection point. Are you looking at the picture like this guy? Like right there? Yeah, okay, so maybe the slope of that one is 1. But I can imagine if the graph were like a little bit steeper, then maybe it'd be like 2 or 3 or 4. Yeah, so I think the slope could be really any number at all at the inflection point. That's a good attempt. Okay, so we set this guy equal to 0 and we solve. And so we get, yeah, x is equal to add 8 divided by 6, or reduced 4/3. Okay, 4/3 is not yet a point of inflection. A point of inflection specifically is a place where the concavity changes. I don't know that it changes at 4/3. I know that the second derivative is 0 there, and maybe it changes on either side, but we still have to do work to figure that out. And this changing that we're talking about is going to be captured in a sign test. So we're going to put 4/3 right there, and we're going to plug numbers in on either side of 4/3 into which function? I've got 3 of them on this board right now. Is it the original? What, f prime? Is it f double prime? What we're after right here is to determine where the thing is concave up and where it's concave down. That's f double prime, right? We're looking to figure out where it's concave up and where it's concave down. Just as a shortcut, anytime you're doing a number line test, a sign test, you are going to be plugging into the function that gave you the number in the first place. Where did this 4/3 come from? It came from f double prime. That's what we're doing the sign test on. It's always that way. Okay, so now we plug in. So if we plug in a number bigger than 4/3, for example, x equals 100, into the second derivative, so plugging 100 in right here, 6 times 100 minus 8, don't do the arithmetic, just tell me if it's positive or negative. That's definitely positive there. And then we plug in something less than 4/3, for example, negative 100. Again, plugging it in, negative 6 times 100, or 6 times negative 100 minus 8 is for sure negative. And so if I'm writing my intervals of concavity, I know concave up means second derivative positive. And that starts where? 4/3 and goes to where? Infinity, forever. And then concave down means the second derivative is negative. Negative infinity to 4/3 is good. If you decided that you wanted to include 4/3 here on the concave upside and also on the concave downside, no problem. No problem. Just be consistent.
So do we know that there's only one inflection point?
Yes, so if you had a fifth order polynomial to start, then the first derivative would be what power? 4. If that was an x to the fifth, it'd have x to the fourth here, and the next derivative would be x to the third. And cubic equations equal to 0 usually have how many answers? Usually have 3. So you'd have more numbers that pop out. Yeah. Okay, so we found our intervals of concavity. Let's also write the inflection point. It is x equals 4/3. We don't know the y yet, but how would we calculate it? Plug 4/3 in. Yeah, plug it in is a really risky thing to say in a calculus class, because there's currently 3 functions up on the board, all of which we could plug 4/3 in and get different pieces of useful information. The original function, right? So f of 4/3. We're not going to do it here. It's just arithmetic, but you just plug 4/3 in everywhere in the f, and that would be your y value. Okay. Suppose for 1 second that we hadn't gotten a minus on this side, but rather it was plus and plus. That means concave up and then concave up again. Is 4/3 a point of inflection in that case? No. Points of inflection have to be where the second derivative changes, where the concavity changes. Okay? So getting 4/3 out here just makes 4/3 a candidate point of inflection, but it isn't a point of inflection until we do that sign test. 4/3 is probably not a max or a min. Yeah, it's probably not a max or a min. Yeah, the max min stuff comes out of the first derivative. Yeah. Okay, all right, we're gonna send you back to wherever you were, and we'll come back together again in like the last 5 minutes of class. So if you're in the activities, go right back there. If you're in the even more practice, you can go there. If you want to try this misplaced number 12 in the even more practice, cautiously take my function here and try to do the calculus on it, and let's see if I did my distributing correctly. Okay, so here we go on page 78 with our third and final demo, just this one last problem. It says, let's find the critical numbers and use the second derivative test to determine whether the critical numbers are maxes or mins, or maybe neither. So the second derivative test is brand new for us. You saw it in the activity today. Okay, so critical numbers means taking a derivative. So let's start there. So we go 3x squared minus 27. And then to find the critical numbers, what do I do with this derivative? Set it to 0. And now we've got a little bit of algebra to do. Totally okay to add the 27 to both sides. 3x squared equals 27. And so x squared is 9. But I've seen people go wrong right here. Is x equals 3 the only critical number? Plus or a minus? Really easy to forget to do that. Plus or minus 3. Those are our 2 critical numbers. Okay, so first I'm going to show you the first derivative test, which is old for us. It will look familiar once we write it here. It means make a number line, put your critical points, just get them in the right order, -3, 3. What function am I labeling that number line with? F or F prime or F double prime? Or sorry, G. G prime, right? Wherever the numbers came from, that's how we label it. And then we just pick numbers in each of the intervals. For example, x equals 100. Plug it right back in right there. So 3 times 100 squared minus 27 for sure is positive. So I'll put a positive thing out here. Between -3 and 3, let's go 0. Plug 0 in. It's -27. Okay, that's a negative. And then plugging -100 in, it is getting squared and becoming positive 100 squared. So it's a big positive number out there. So what all of that means to me is that the original function g is increasing because g prime was positive, and then decreasing, and then increasing. And so -3, is it a max, a min, or neither? That is a max. It is going up and then coming down. -3 is a max. And then going down and then coming up. 3 is a min. Okay? That right there, everything in green is called the first derivative test, and the final conclusions are max at -3, min at 3. That's it. But instead of doing that, we could do the second derivative test. It is going to answer the same exact question and is going to come to the same conclusion, that -3 is a max and 3 is a min. So it's not like you do this one too. It's just another option for you. Okay, second derivative test. Clearly we need to calculate a second derivative, so let's do that. Okay, what is g double prime? 6x. Okay, and then we take our second derivative and we evaluate it at the critical points. We don't set it equal to 0. We evaluate the second derivative at the critical points, which we found up above there in blue and black. So if I do g double prime of -3, I'm going to get some number. And if I do g double prime of +3, I'll get some number. So when you plug -3 in, what do you get? -18. All I care about is whether it's positive or negative. And when I plug 3 into the second derivative, we get 18. Again, all we care about is positive or negative. Based on everything that's up there in orange, we are supposed to be able to look at that and decide whether -3 is a max or a min, and decide whether 3 is a max or a min. And so you filled in some blanks on the previous page, but I don't have it memorized. I just have a visual. I know that I'm sitting at one of these two pictures. It's either like a smiley face or a sad face. If the second derivative at -3 is negative, that means that we are concave which way? Down. That means I'm in this picture over here. Am I looking at a max or a min or neither? That is for sure a max, just because concave down right there. So that means that this guy is a max. G double prime of 3 is +18, concave up or down. Concave up, that's my smiley face. Is that a min or a max? That is a min. So you choose either green or orange. Frankly, orange was pretty easy in this case, wasn't it? We don't have to do a sign test. We don't have to plug in 100, -100, and 0. We just had to plug in simple numbers into a simple second derivative. But again, the conclusions are exactly the same. Right? First derivative test or second derivative test, both solve the same kinds of problems. Tell me where the maxes and mins are. Okay? All right, so that is the end of all the stuff that's going to be on the test. When we come back in on Monday, it's our review day, but I will just point out that if you go a few pages away, you want to get started, there's a study guide right here on page 83. Long list of things that I want you to be able to do when you come in for that test Wednesday, and then after that, you'll find a simple test. Yes?
Oh yeah, two things. First, do we ever have to actually use terms up on the board? Like, oh, it's good.